can solve these types of LPP using simplex method or using graphical method. How to solve this problem using graph? First draw the graph, that is draw a line for each constraints. Then identify a feasible region. Then find the optimal solution using corner method. List out all the points that form the feasible region. Then calculate Z for each point. Choose the point with the maximum Z value if the objective is maximum profit. So these are the steps involved in this graphical method. So one question, solve the following LPP using graphical method. Our question will be this one, Z equal to 70t plus 5c 50c subject to 4t plus 3c less than or equal to 240, 2t plus 1c less than or equal to 100, tc greater than or equal to 0. So we have two constraints. We have two lines. This is the first line and this one is the second line. To draw the line, we need to obtain 2 points. So first of all, take the first line. That is, this one is the first line. 4t plus 3c less than or equal to 40. Put t equal to 0. We get z equal to 80. So point is 0, 80. Then put c equal to 0. We get t equal to 60. So point is 60, 0. So we got 2 points for this line. We can plot the line. Again, take the next line, it is next constraint 2t plus 1c less than or equal to 100. From this t equal to 0, we will get c equal to 100. Point is 0, 100. Again, c equal to 0 means we will get t equal to 50. So point is 50, 0. So we got 2 points and connect them with a line to obtain the graph. So for the first line, this is our first line. This is our first line. First line is represented using this blue line and the next line, this line, 2t plus 1c less than or equal to 100. This is represented by this green line. So we got points for first line are 0, 80 and 60, 0. Oh, okay, what is the next step? We need to identify the feasible region. Feasible region is the region that contains the solution. So we have, for the first line, we have less than or equal to. So less than or equal to means in feasible region, the less than or equal to of the constraint indicates that the feasible region lies below or to the left of the line. So our line is this blue line. So this magenta shaded region are the feasible region of that line. Again, the next line, green line. Green line means 2t plus 1c less than or equal to 100. For this line, we got this blue line, this blue shaded region. So, feasible region is the overlapping region among the lines. So, finally, we get this red line as the feasible region. Now, we need to find the optimal solution. Optimal solution means we had identified these points. We know this point, that is 0, 80. Again, this point is unknown because this is the intersection point. Again, this point is 50, 0 and this point is 0, 0. So we get a polygon like this, 0, 0, 0, 80, 50, 0. This point is unknown. This is the point of intersection between line 1 and line 2. To find the point of intersection, you need to solve the equation and the point is 30, 40. Now we need to calculate the Z point for all the points. So we have 4 points, 0, 0, this is 0, 0 and 0, 80. Intersection point is 30, 40, then 50, 0. Corners of the polygon. So find the Z value. Substitute the value of t and c, we will get the Z values. Z values will be like this. So now we need to choose the maximum Z value. For maximum Z value means this is our maximum Z value. So optimal solution is t equal to 30, c equal to 40 and Z equal to 4100. Next, a simple question. Maximize 2x plus 5y subject to x plus 2y less than or equal to 16, 5x plus 3y less than or equal to 45, xy greater than or equal to 0. So, using extreme or corner point method. The approach we had discussed in the previous problem is extreme or corner point method. So these are our decision variables. X and y are the decision variable and this is our objective function. So these are our constraints. So we have two constraints C1 and C2. So this is our non-negative constraint. So to finding the points of the line, we have the constraint x plus 2y less than or equal to 16. So we need to find a point. Putting x equal to 0, we got 8. Putting y equal to 0, we got 16. So first line is plotted here, that is uh, 0, 8, 0, 8 and 16, 0. These are the 2 points of the first line and it is plotted. Then take the second line and the points are 0, 15, 9, 0. So this green one is the second line. Now we need to plot the feasible region. These are the feasible regions of second line and these are the feasible region of first line. So in general, we will get this is our feasible, this is our intersection region, this blue shaded portion. This is our feasible region. Now we need to identify all the corners of this polygon. The rounded regions are the corners of the polygon. We need to find the values of these corners. So we already know these 3 points. This point is unknown since it is an intersection. So we can solve the two equation. This is the first equation and this one is the second equation. From this we will get the value of. So optimal solution is, so we got the optimal point. Optimal point is 6, 5. Now we need to find the z values. For each and every point 0, 0, 0, 0, 0, 8, 0, 8, this is 6, 5 and this is 9, 0. For each and every point in the corners of this feasible region, we need to find the z value. Okay, after finding the z value, maximum value is for this point. So this is our optimal solution, x equal to 0 and y equal to 8. Another question. Minimize z equal to 5x plus 7y, x plus 3y greater than or equal to 6, 5x plus 2y greater than or equal to 10, y less than or equal to 4, xy greater than or equal to 0. Solve the LPP model graphically. So actually the graphical method is limited to two decision variables. Here only two variables are there, so we can solve this using graph. So this is the first constraint, this is the second constraint, this one is the third constraint. So for the first line we got 2 points, for the second line we got 2 points and these two lines are plotted. Again the third constraint is y less than or equal to 4. This line is also plotted. So we got a feasible region like this. Now we need to identify the corners A, B, C. We already know these corners. But we cannot calculate this point. So how will you calculate this one? Move the objective function line parallel to itself. Line passes through A and C and B is the optimal solution.